Hi, I'm Anurag, and I'll be telling you about Qruise. So we build machine learning software, and the machine learning software is for accelerating how we do scientific R&D, and we're starting with quantum technologies. So the problem we are trying to solve is that developing any new physics-based hardware technology, for example, quantum computing, quantum sensing, is extremely hard and slow. And the reason that we see it like this is primarily because of two reasons. One is that you don't have the kind of faithful simulation and modeling tools that exist for a more mature technology, like semiconductor chips or automotive devices. And this process is extremely manpower heavy, so you need to hire as many physicist PhDs that you can get and put them in a room for a few years, and hopefully they come out with a quantum computer. So that's the challenge we're trying to solve. And what do we have right now in the market? How is it tackled right now? So the tools that we have right now in the market, they're very good and very robust at providing simulations and modeling for existing technologies. And they can do this, but they don't incorporate data into this whole simulation process. And it works very well for existing technology, and it's dominated by companies from 70s and 80s. So think MATLAB, COMSOL, ANSYS, all companies built during that period. But the good thing is that this is a huge market. This is a $20 billion per year market if you take all of these companies together, and we're talking about the high-end numerical simulation tools market. And good for us, this is not built from the ground up to support machine learning and AI technologies. So this was built at a time when data was scarce, when AI and ML technologies were not around. So this is very ripe for disruption because they're simply not built to be ML first. What are we proposing? So the tool that we provide in a very precise manner to summarize, it's something like a co-pilot for physics R&D. And the problems or challenges that it helps to solve is that when you have this research and development cycle, you are essentially bottlenecked by how much effort you can put on various different tasks that you can improve. So if you have 5 different things to improve, you want to be able to figure out which is the most valuable thing that you can work on so that you get very large improvements on your bottom line metric. And that's really the whole job of identifying these bottlenecks. Once you identify these bottlenecks, you want to be able to very quickly optimize between your design iteration. So this whole loop that you see here, the faster you can do this loop, where you go from design to fabrication to characterization and then back to the next design, that's how far you can go, how fast you can go from generation 1 to generation 2 to generation 3. Right now, for hardware technologies, it can often be that you can only do 3 to 4 iterations in a year. But if you think software, that can easily be a few iterations in every couple of months. So that's what you want to speed up. And you want to be able to use data-driven decision-making to do this. And that's really where we help to incorporate data into your simulation and modeling tools. And that lets you do this whole cycle up to 3x faster, which immediately translates not just into reduced manpower effort, but significantly faster time to market. So how do we actually do this? So there are 3 particular aspects of the technology that we develop which lets you do this. The first part is this extremely accurate digital twin that we develop, and this twin is not something that is static. It is not defined by physicists from first principle, but it's actually something that learns from data. So it's a digital twin that's extremely close to your experiment because it's something that is constantly learning from data and understanding how to model your systems closer to reality. And once you have that, we provide you the tools, we provide our users the tools to characterize the systems very fast. And like I said, our go-to-market is quantum technology, so this is already in play over there, where we provide these tools for quantum computing and quantum sensing devices. And this very fast characterization is a bottleneck right now, because a very good example to think about is how long it takes IBM to announce a quantum computer and then actually put it on the cloud for users to use. It can easily be several months, and the main bottleneck behind that is how fast they can do calibration and characterization. The killer application, however, is the predictive model that we provide. So this physics-based machine learning model that we provide, this has this capacity to predict that these are the A, B, C things where you should focus on, because these are the factors which will give you 2x, 3x improvement in your bottom line performance. Because then you know how to allocate your assets, your R&D asset, to accelerate your R&D process. So who are our customers and how do we make money? So we basically sell to anybody who's making hardware. And right now, that's quantum hardware, so quantum computing, quantum sensing hardware. It could be academic labs, it could be industrial players. And we sell software licenses, very straightforward business model, annual licenses. We also have basically a very flexible deployment model. You can use our software in the cloud, or you can use it on premises, and that's very relevant because our customers are IP sensitive, so they care about having things within their firewall. And we also partner with various other sales channels. So we partner with electronics manufacturers because they are ubiquitous in all of these user groups. So we go directly through them to our customers. Why quantum, you might think? Well, primarily because a lot of us come from that background, but from a more strategic perspective, that's because it's an extremely underserved market. So we can provide the tools in a market which doesn't have players right now from the established portfolio, and it's growing very fast. We have users who are currently using our software, both in academia and industry, and we expect to diverge into new fields like silicon photonics and MRI, where we're actively exploring partnerships right now with early players. We were founded less than 2 years back. The team is 20 people, mostly physicist PhDs, and we have validation. Revenue we expect in early next quarter, let's put it that way. We have adequate grants to keep us going till 2026. So we're not raising actively right now, but happy to chat with investors. That's all.
You mentioned digital twins. So the front side is typically simulation, the back side is measurement or operational. So can you give me a little more color on how you make those two come together?
Right. So our software is essentially designed to live very close to the hardware, which means it directly interacts with the hardware and it collects data. Once you collect the data, our digital twin is learnable. So it's basically a machine learning model where you can feed the data, and the parameters of the twin get updated based on the data. So we basically do model learning on experimental data where the twin learns from the data.
And so if you're getting data from a real-world device, then just you connect through API to various sets of instrumentation.
Yeah.
Can you give me a flavor for what sort of measurements you're making that you gather data from?
Right. So depending on the kind of device we're working with, so whether it's a quantum computing or a quantum sensing device in this case, these are typically either a list of textbook experiments like Rabi, Ramsey, or these experiments that most people perform. But one of our secret sauce is also that we develop these adaptive experiments where the digital twin basically designs a custom experiment for this hardware, which is optimized for certain parameters of interest. So if you want to learn certain parameter, it's not a human professor sitting there and designing an experiment, but rather the software algorithm figuring out that this particular pulse is optimized for information gain to learn this particular parameter.
Yeah, I guess I have a related question. Maybe you answered already, but how do you do the training for your algo? I mean, is it specific to the kind of asset that you're analyzing, or is it kind of universal across the platform?
Yeah, so it's actually universal, and that's something that we wanted to focus on from the very beginning. So we have essentially a differentiable digital twin, which means that you can feed it whatever data you want from any different experiments you want to run, and it will use the collection of that experimental data to learn the best model which fits the data. So there is always the limitation that you need to be having the data in the first place, but once you have the data, you can feed that into the loop to get a very good model.